on what we have done today. So at the outset, I just want to put this chapter, which is chapter 5, in perspective. Last time I gave you a roadmap of what we'll be doing for the entire semester. So we have talked about control volume, what we have done for the past month, a global average approach, and then we can get some rough estimate of forces. And then today we look at differential analysis. There are a lot more to come, which are the tools that you will use to solve real engineering problems. Then you have experimental verification. Doing a test to make sure what you analyze is correct. And all engine devices have to go through this testing. I don't care if it's a hydraulic turbine or an aircraft carrier or a Boeing 787. You do all the analysis and that's what you pay for. You don't know you're right or wrong. There are other unknowns that will change your analysis. So testing is essential. Question is, what do you test? Can I test a scale model? Instead of full-size 77, the size of a football field, can I shrink it down by 20 times? When the wind tunnel needs to went off and get some data. And how do I know I'm correct? That's what we're doing here. Experimental verification. By way of inexpensive testing. This statement is going to be relatively vague until we use an example which is flow in the pipe to illustrate what I meant by that. But the importance of this so-called dimensional analysis is simply allow me to simplify the problem. How? By reducing the number of variables. So instead of a problem that is dictated by 10 variables, velocity, fluid, size, you name it, I want to see if there's a way I can shrink it and make it less than 10. Make it 7, for example. And if I succeed in doing that, I will reduce my test matrix considerably. How is to be determined next time. And the relatively vague idea of reducing the variables using a grouping technique can only be illustrated by example. Right? So what we're set out to do is to look at the physical problem, like the flow in a pipe, which has variable like velocity, fluid property, diameter, length, you name it, and I'm charged to estimate the pressure drop. All of which you have seen in MD 2124. Can I reduce the problem to something smaller in scope? So when I do my testing, I don't have to do it in air, and then water, and then oil. Because that's 3 experiments. It's a lot more work. I want only do one. The question is how. Right? So the basis of this dimensional analysis go back to our fundamental mass, length, and time units. So I want to revisit that very quickly, because that will be our starting point. So I have, prior to test one, we visit this concept of mass, length, and time. And for dimensional analysis, this entire chapter 7, every quantity of secondary nature, by that I mean derived properties, like density, force, pressure, can all be expressed by way of mass, length, and time. So the secondary property are all derived properties. Viscosity, for example. Example is just simply density. And I will finish with this last statement, and next time we come back, I will expand on that. The concept of dimensional analysis is simply based on this law of common sense. Dimensional homogeneity. Meaning, give me an equation, momentum, energy, Bernoulli, all terms in that equation must have the same unit, or it's not physical. And we're going to take advantage of that. In layman term, this translates to each term has the same unit. I'm going to tell you, I'm going to take advantage of that and use that insight to reduce my variables in any problem by 3 terms. Those are the mass, length, and time. So that I formulate a dimensionless equation, which will help me to reduce the complexity of the problem by 3 times. Okay? And that's the goal of what we're trying to do in chapter 7.